Okay, students. I'm going to do this a little different than I've done it in the past. Since your quizzes are set up in chapters of threes, in other words, chapter 1, 2, and 3, and then your quiz, chapter 1, 2, 3 quiz, chapter 4, 5, 6 quiz, and so on. I'm going to do your problem solutions that way. So we're going to start with chapter 1. Now, I'm not going to work every single problem. At the beginning of the semester, do not forget about the email that I sent out for all 12 chapters that we're going to do this semester. I gave you the problems at the end of the chapter that you need to be working on. And by the way, they are in the problems section of the end of the chapter. And your conceptual questions might not hurt to look over those at the end of the chapter, because you'll see a few of those on your problem quizzes and on your midterm and final exam. Okay? All right, so make sure you remember that. And, I'll send that email out probably on the first or second day of class, more than likely the first. Okay, so let's look at chapter 1, and I decided I'd probably just work 4 problems from each chapter. And another thing, too, I want to remind you is when you go into your class in Blackboard, you'll notice there's a tab that says Study Area. You can click on that and go through each chapter, and you can watch lecture tutorial, or lecture demonstration videos or tutorial videos on the chapter. And they're typically, usually fairly short, and they're really, really good videos. And then you also will see that there are solution videos, and they don't do all the problems, but they pick several problems out of the chapter, and it'll tell you which one it is. And they work those problems on video. So if you're having a little trouble with a problem and it's one of those in those videos or one of mine, you can watch my videos or go watch the videos that came with the textbook. And they're really good, too. They do a really good job explaining the problems. Okay, so let's look at chapter 1. And the first problem I want to look at is problem number 4. Now, you've probably already noticed that the end of the chapter has the solutions for all the problems, but only, if I recall, it only has the odd-numbered solutions. Yeah, so if you go to the end of the book, go to the appendices, you will see that you have the odd number problems answered in the back of the book. They don't have it worked out, but just the answer, so you can check yourself, okay? So number 4, it says in figure P, 1.4 shows Sue along the straight line path between her home and the cinema. What is Sue's position, X, if A, her home is the origin, and then B, the cinema is the origin? Okay, so basically what this has to do is being able to orient yourself based on a particular position. Basically what we're looking at is Cartesian coordinates here, okay, or a number line in this case. And so we have Sue's home here, okay. So here's the home, and you do need to always draw these problems. And then here's Sue, and Sue, she is about 2 miles from her home, okay, so 2 miles, all right. And then you've got the cinema over here, cinema over here. And so this distance from here to here is 3 miles, okay. All right, and then the question says, question 4A, it says, what is Sue's position, X, if her home is the origin? So if her home is the origin, then this would be 0, this would be 2 miles right here, would it not? Because from here to here is 2 miles. So then her position would be a positive 2 miles, okay? She is 2 miles in the positive direction from her home, okay, because the home is the origin. Then if you look at part B, it says, well, what if the cinema was the origin? Well, if that's the case, then basically what you've done is you've flipped everything around here, okay? You flipped everything around. I hate it when I do that. Doggone it, okay? You flipped everything around, and now this becomes the origin, so that's 0 miles. And so now we're going to the left of the origin, and so it would be a negative 3 miles, wouldn't it? Okay, so if you remember when you did work with number lines in junior high and high school, anytime you go to the left of the origin on the x-axis, it's negative, and anytime you go to the right of the origin on the x-axis, it's positive. Just like on the y-axis, if you go above the origin on the y, it's positive y. If you go below the origin on the y, then it's negative y, okay? All right, so you should remember that from doing number lines in junior high and high school and in algebra, okay? All right, the next one we want to look at is number 10. Oh, by the way, that was on the questions. This one was on page 28, okay? And the questions actually the problems start on page 27, okay? So on page 28 was number 4 and also number 10. So then this is chapter 1, okay? Chapter 1 problems, all right? And so now let's look at number 10, and this is also page 28, okay, still on page 28, and says a security guard, okay, I want to make sure I always look at my notes too, okay, a security guard walks at a steady pace, traveling 110 meters in one trip around the perimeter of the building, okay, so you got a building here. And so the security guard, and I'm not drawing it 3D, but we'll pretend, okay, it's 3D. So he goes all the way around, okay, goes all the way around the building, and the perimeter, okay, perimeter is 110 meters, correct? Okay, I thought that's what it said, yeah. All right, it takes him 240 seconds to make this trip. So the time, so we could write that down as D. D is equal to 110 meters, the distance, and the time, T, is what? 240 seconds. This is a really easy problem. So then it says, what is his speed? Now, if you've already been looking ahead in the chapters, we define speed. Speed and velocity are very similar. The only thing with speed is if you take my calculus class, we talk about scalars and vectors. Speed is a scalar quantity. Why is it a scalar quantity? Because it only has magnitude, all right? It does not assign a direction like north, south, east, and west, okay? So it only has magnitude, whereas velocity has magnitude and direction, all right? Velocity is a vector quantity, whereas speed is a scalar quantity. You say, I'm going 50 miles an hour right now down the interstate. That is a speed. That's a scalar quantity. But if you say I'm going 50 miles an hour south down the interstate, then that becomes a vector quantity, okay, because you give magnitude and direction. So we would say, we could write it this way and say that speed is equal to the distance traveled divided by the total time of travel. And so that's what, 110 meters divided by 240 seconds. And so his speed then is what? His speed is 0.46 meters per second, okay? So though the units of speed and velocity are the same, they're not the same quantitatively, okay? Well, they might be the same quantitatively, but as far as direction is concerned, they're not the same, okay? You can go in a circle and then walk the same distance in a particular direction and get the same number, but you're not going to wind up in the same spot, okay? Notice here he came back to the origin, all right? What if he walks straight for 110 meters, all right? Well, then he's going to wind up in a different spot. He's not going to go around the building. He's going to go away from the building. Okay. All right, so let's move on now. All right, so number 16, and 16 is also on page 28. I didn't assign a whole lot of problems out of chapter 1. There's chapter 1 still. So let's look at number 16, okay? So number 16, I think we're doing some conversions here. It says convert the following to SI base units. So we're wanting to convert to SI. So convert to System International, okay, or what we call the metric units. And so they're asking you to convert to the base units, which would be seconds. So the base units, and what are the base units? Meters, seconds, grams, or kilograms. You could actually say it either way, kilograms or grams, just according to, well, no, I take that back. The base is gram. Ooh, I don't know what I'm saying. I almost messed up there, didn't I? It's been a long day, y'all. It's after 3, and I'm recording these videos. Okay, so you got meters is for distance, seconds, grams. Volume is going to be liters, okay, and so on, all right? But those are your base SI units. So we got to convert 9.12 microseconds to seconds, right? Okay, so how do we do that? Well, we do our dimensional analysis, our factor labeling, so microseconds. Well, what is a microsecond? Well, 1 second is equal to 10, hang on a minute, I'm doing this backwards. Doggone it, I'm writing it backwards. All right, so 1, well, if I get it back in the pen, 1 microsecond is equal to 10 times, I'm going to get it right in a minute. Here we go. 1 times 10 to the negative 6th seconds, okay? All right, and so our microseconds cancels out, and what are we left with? We are left with 9.12 times 10 to the negative 6th seconds. That's a very, very small time quantity, amount of time, isn't it? Quantity of time, okay? All right, then B, it tells us to do, asks us to do what? We've got to convert 3.42 kilometers, excuse me. We've got to convert it to what? Meters, right? All right, so let's do our dimensional analysis, 3.42 kilometers. All right, and we know that 1 kilometer is what? 1,000 meters, isn't it? And you say, well, Mr. Shields, can we use that King Henry died while King Henry died while drinking chocolate milk? Yes, you can. You most certainly can. You can use that little acronym there and set up that little chart and use it that way if you want to. But you need to understand what the values, in other words, you need to understand that 1 kilometer is 1,000 meters, okay? 1 gram is 1,000 milligrams, okay? You need to remember that. You need to know that. It's based on powers of 10, the SI system is, okay? So our kilometers cancel out. We're left with what? We'll move the decimal 3 places to the right and add a 0, and you got 3,420 meters, or we would write it in scientific notation like this, times 10 to the 3rd meters. You'd write it in scientific notation, preferably, okay? 3.42 to the 3rd meters, okay? And then we look at C, 16C. All right, 16C, we got to do what? We got 44 centimeters per milliseconds, okay? Ooh, that one's getting a little more challenging. So we've got 44 centimeters per milliseconds, and so we want to go to what? We want to convert to meters per second, don't we? All right, now it doesn't matter which way you start or what you start with, okay? It doesn't really matter. All right, let's do it this way. Let's just go ahead and say 44, and let's put our units here, centimeters per milliseconds. All right, we're going to factor label this thing now. All right, so how many centimeters? We know that 1 centimeter, it's on the top, so this has to be on the bottom. You say, how do you know to put that there? Centimeters on the top, so the conversion factor for the centimeters, 1 centimeter has to be on the bottom, is 100 meters, right? And then 1 millisecond, right? Milliseconds on the bottom, so my 1 millisecond has to be on the top, so it'll cancel out, is equal to what? 1 times 10 to the negative 3rd seconds, right? Okay. All right. And so, what cancels out? Cancels, and we're left with meters per second. And so we get an answer of what? We get 440, okay? Did I do something wrong? Something does not look right. No, I've got it right. Okay, yeah, I got it right. Okay. All right, so it's what? 440 meters per second, or 4.40, or 4.4 times 10 to the 2 meters per second, okay? For some reason, that's looking crazy. So 44, that's 4,400, yeah. No, 44 times 100, yeah, 44 times 100. Yeah, 4,400 divided by 1. Yeah, I knew that wasn't right. I knew that was way off. That is not right. My apologies. All right, so you multiply 44 times 100. Oh, I know what I did. I see what I did. I'm crazy. I told y'all it's a long day. My bad. All right, 1 centimeter is 10 to the negative 1 times 10 to the negative 2 meters. There we go. All right. And so we get 440 meters per second, or 4.4 times 10 to the 2 meters per second. I had my number wrong up there. All right, sorry about that. Okay, good. Good. All right, and then let's do D, 16D. And it says we got 80 kilometers per hour, so we're going to go 80 kilometers per hour, all right, converted to meters per second, okay? All right. Okay, so let's factor label this thing. So we got 80 kilometers per hour, and we know that 1 kilometer is 1 times 10 to the 3rd meters, or 1,000. And we know that 1 hour is 3,600 seconds, okay? All right. Yeah, 1 hour is 3,600 seconds, okay? So we multiply 83 times 1,000, 80 times 1,000, we get what, 80,000? Okay? And then we divide 80,000 by what, 3,600? And we get what, 22.2? We get 22.2 meters per second. Okay? Very good. All right. And that's number 16. And then let's look at one more. Let's look at number 26. And it's still on page 28. This is chapter 1, page 28, number 26. Okay? So number 26 says Loveland, Colorado is about 18 kilometers due south of Fort Collins and 31 kilometers due west of Greeley. Okay, so we got Loveland, Colorado, and it is what? 18 kilometers due south of Fort Collins. Okay, all right. So this is FC, Fort Collins, and it is 18 kilometers, and that's going that way, due south, all right, and 31 kilometers due west of Greeley, okay? So 31 kilometers, that actually needs to be a little longer, and this is Greeley over here, right? So Loveland is 18 kilometers due south of Fort Collins, okay, and 31 kilometers due west of Greeley. What is the distance between Fort Collins and Greeley? So we want to find that distance between Fort Collins and Greeley, right? Okay. All right. So let's find that distance, okay? Well, we've got, and let's see now, that was in kilometers, right? Yeah, that was in kilometers. All right. Am I reading the right problem? Know if I am or not. I think I am, yeah. Okay. All right, yeah. There we go. All right. So we want to know what the distance is between Fort Collins and Greeley. So from here to here, we want to know that right there, don't we? This is what's question mark, right? All right. Well, we know is it Loveland? Yeah, Loveland is 18 south of Fort Collins, and Greeley is 31 west. Okay? All right, so we got to find the hypotenuse, don't we? Well, that sounds like a Pythagorean theorem, doesn't it? we know that a squared plus b squared is equal to c squared. And you say, how did you know to do that? Because it's a right triangle, okay? It forms a right triangle because it said due south and due west. That makes a perfect right angle. So to find the distance then, so the distance to from FC to Greeley is done by what? Taking the square root of the squares. So we got 18 kilometers squared plus 31 kilometers squared. And so what do we get? Let's do the math real quick. Okay, so we get 18 squared plus 31 squared equals, and then take the square root of that. And you should get something like 35.85. So that is equal to, so the distance from Fort Collins to Greeley is 35.85 kilometers, or you could just say 36 kilometers. You could round it up. Okay. And really we should, using our sig fig rules, because two significant figures, that should be two significant figures, okay? Use the sig fig rules, okay? All right, that's all in chapter 1. And I'm going to pause a minute so I can get ready for chapter 2. So I'm just going to pause. Be right back. Okay, students, we're back. And let's go ahead and pick up now on chapter 2. In chapter 2, we're going to do 4 problems. Let's look at number 20. And this is on page 66, year I was born. And so it says figure P.20 shows a graph of actual position versus time data for a particular type of drag racer known as a funny car. All right, so basically what we've got here is we've got a graph. It looks something like this. And of course this is 0, and then we got 100, and then we got 200, and then we got 300, and then we got 400. Okay, and then you've got 2 seconds, and then I'm trying to do this as best I can, 4 seconds, and then 6 seconds. All right, and of course you got a line here, and a line here. I'm trying to draw as straight as I possibly can. Then you have a line across here, and a line across here, and here, and there. Okay, and our graph looks something like this. Okay, so it starts out kind of flat here, and then it curves up, and then it does something like this right here. Okay, like that right there. So what you really have to do is you have to think about, all right, I got to think about math here. So we're going to go, it says estimate the car's velocity at 2 seconds. Notice it said estimate. So right there is 2 seconds. So what we're going to need to do then is we're going to need to draw a line tangent to that, okay? So we're going to go from here, and we're going to pass through this point, and we're going to, and notice where this is going to come out. It's going to come out at about 1. And then we're going to go all the way up here to 4 seconds, okay? So a straight line, and that's not straight, but it's close enough. And so for position A, if you remember, how do we determine the car's velocity? And actually what we're doing more or less is average velocity. Actually, it's kind of like taking the tangent of the slope, okay? All right, so, okay. All right, and so you read your dotted line, and that, like I said, this would be 1 second, and this would be 200 seconds, but it's, let me look at the graph, and I'm thinking the graph, no, actually on the graph it's about 3.5. So right here, this one's going to be, this would be about what? That would be 200, so that's going to be about 3.5 seconds, isn't it? So if you remember that velocity is equal to the change in displacement over the change in time, well, what's our time interval? Our change in displacement is what? Our change in displacement is from, the final would be what? 200. So we got 200, minus 0 meters divided by, well, we got what? 3.5 seconds minus 1 second. And that's going to be equal to 2.5 seconds over 200. And my answer may be just a tad different than what the book may show you. Well, no, the answer's not in the book on these. That's right, it's an even, all right? So we got what? So we got 200 divided by 2.5, and you should get around 80 meters per second, okay? 80 meters per second, okay? All right, 80 meters per second. All right, and then we do the same thing for part B, so 20B. All right, now I'm going to go back to this same graph. I'm not about to go through all the headache of drawing that again. Then we got to do it for 4 seconds, don't we? Estimated at 4 seconds. So at 4 seconds, we're right here, okay? And so we're going to go from where to where? All right, so at 4 seconds, we're going to go all the way up to what? About 5 where it touches this line. So dot, 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 dot. So it's pretty straight in it. So from 5 to what? 5 down to what? All the way down to 0? Will it go all the way to 0? No. It goes down to about, it goes down from where, all right? So a straight line would be what? All the way down to 2 seconds, wouldn't it? So we're at 400. 400 is our maximum extent. So we would read this point here and this point, this point right here. So that's going to be what? So 400 minus 100 is equal to 300 divided by, and we've got what? It was 4 seconds down to what? 1 second? All right, we come all the way down. So it's, 5 seconds. That's 5 seconds. All the way down to what? 2 seconds? Yeah, 2 seconds. Okay. I'm sorry, I wrote 4. I meant 5. So 5 minus 2 is 3, and that's equal to what? So that's going to be 3, and that's going to be 100 meters per second. Okay? All right. But again, that's estimation, and I don't really like it when they give you estimation problems, but there they did give you an estimation. Okay. All right. Okay. Now let's look at problem number 24. We'll go ahead and go to another clean slide. This is chapter 2 still, and it's on page 66. All right, let's look at 24. All right, so 24, it says what? Oh, figure P 2.18 show data from the speed of blood in the aorta. Determine the magnitude of the acceleration for both phases, speeding up and slowing down. Okay. All right, so you have a graph, and it's drawn something like this right here. Of course, that's 0. And you've got 0.5, and then 1.0, and you've got a line going across here, and you've got a line going across there. And then you've got what? 0.2, 0.4, and then 0.6. And of course there's a line coming straight down here, a line coming straight down there, and a line coming straight down there. That's pretty symmetrical. Okay? And it goes from point 2, it goes up this far and then down like that, doesn't it, to point 4. Okay, so let's look at that. So notice we go, this would be 0.3. Actually, I've made that a little bit too flat. See if I can do it a little bit better. It's actually, it's actually pretty steep. And it comes down like that. Well, this right here would be 0.3. So actually it goes from 0.2 to 0.25. This would be 0.25 seconds right here. And this would be what? Well, that's 0.5. Halfway in between 0.5 and 0.1 is 0.75, isn't it? And that's in what? Meters per second. So this is meters per second, and this is seconds down here. All right, so for the acceleration, we know the acceleration is equal to what? The change in velocity divided by the change in time. Okay, v final minus v initial divided by t final minus t initial. Delta means change in. If you want to write it this way, V final minus V initial over T final minus T initial, okay? Or if you want to use 1 and 2, or if you want to use naught, which is initial, and then nothing, like this would be V minus V naught, or T2 minus V2 minus V1. I like to use F and I, okay? All right, so we got to find the acceleration for this going up. So notice that from here to here, well, what's my final? All right, well, let's look at it, all right? So the acceleration is equal to, all right, look, the final is 0.75. So 0.75 meters per second. What was the initial? Well, it was 0 meters per second. And then my final time was 0.25. And my initial time was 0.2. And so we do what? 0.75 divided by 0.05 is equal to what? 15 meters per second squared. Now notice the units changed. Now to remember, if you watch the lecture videos, that acceleration is the rate of changing velocity, okay? The rate of changing velocity. So it'll be 15 meters per second for going up. And that's going up. And then when it's coming down, acceleration when it's coming down, okay? And I think that's what it asked. Yeah, when it's slowing down, okay? All right, so we do the same thing. So from here to here. All right, well, the initial, the final is what? 0. The initial was what? Minus 0.75 meters per second. The time was what? Well, the final time is 0.4, and the initial time is what? 0.25. All right? That should be right. Okay? 0.25. So that gives you a difference of what? 0.15? And so we get an answer of what? What's the answer going to be? The answer is going to be a negative negative 5 meters per second squared. You say negative? Yeah, look, right here. See the negative right there? Because the final is 0. The initial is 0.75 right there, okay? All right, hope that helps there. And now let's look. I think I've got one more. How many is that? Or two more? Okay, this is the third problem, yeah. So this is number 35, and this is still chapter 2, page, and this is page 67, okay? All right, so let's look at number 35. And it says, Formula One racers speed up as much more quickly than normal passenger vehicles, and they also can stop in a much shorter distance. A Formula One racer traveling at 90 meters per second can stop in a distance of 110 meters. Okay, what is the magnitude of the car's acceleration as it slows during braking? Okay, so what we need to do, we got our race car here, and so we got our race car here, Formula One. All right, and there's a dude driving right there with his helmet on. Okay. All right, and so he's going to go from here to here, and he's going to stop right here. Okay. And so the stopping, it tells us that the stopping distance from here to here is 110 meters. So we're going to call that the change in x is equal to 110 meters. Starts out initial meters, 0 meters here, and then 110 meters there. So delta x, the change in x, will be 110 meters, okay? All right, I hope you're with me, okay? All right, that's change in x. And then we know the initial velocity, or excuse me, you say, well, how do I know which is initial and final velocity? Well, it tells us that the velocity of the car is 90 meters per second. So that would have to be the final velocity because it's going to stop. Okay, or excuse me, that would be the initial velocity. I'm sorry. So the initial velocity, because it tells us it's initially at what? You say, well, how do you know it's initial? Well, it tells us 90, and then it tells us it's going to stop. Well, where's the stopping velocity at? Well, that's when it quits moving. That's when it stops. So that has to be initial. 90 has to be initial. And what's the final velocity? Well, it stops. It doesn't have any, so it's 0 meters per second. Okay. All right. Now, some of you are saying, now, how in the world am I going to find acceleration? See, I got to find the acceleration, right? And by the way, acceleration can be negative. We just calculated one where it was negative, okay? It can be negative. Even if you got a positive velocity, you can still have negative acceleration. All right, now, okay, so how do we do that? Well, if you go back and you look in your lecture videos and looked at the equations, the kinematic equations, we have this equation. V final is equal to V initial plus 2A delta X, okay? This is a very useful equation because it doesn't have time, or it does not require the use of time. Time has actually been substituted for, and the equation was solved to get this. And if you were to take my calculus physics class, I would show you how that is derived, okay, how we come to that equation, all right? But we're not going to have to worry about that in here. All right, so let's look at everything then. So first thing we need to do is solve the equation for acceleration. So we get acceleration is equal to what? Well, it's what? It's V final squared, by the way, it should be squared minus V initial squared, and subtract VI from both sides, and then divide by what? Delta X, right? Now delta X is X final minus X initial. So we solve for the equation A, and we plug in, well, what's the V final? Well, V final is 0. All right, so that's 0 squared is 0 minus, now listen, this is not minus 90, it's minus parentheses 90 squared. Okay, do the math. Think about your order of operations. Okay? You're not making velocity negative, you're subtracting the initial velocity. Okay? It doesn't make it negative. You got to be careful there now. Don't forget your algebra. Okay, and then divided by what? Well, the delta X was 110 meters. All right, and so what do we get? So we get 90 squared. So 90 squared, and it's negative, but we'll put that on in a minute. So 90 squared divided by what? 110. And what do we get? We get, no, why does that not look right? What in the heck have I done wrong? Oh, shoot. Shoot. I forgot the 2 there. It's 2 times that. Whoops, my bad. So it's 90 squared divided by 2 times 110, and you get 36.82 seconds. Negative 36.82 meters per second squared. Now it's negative. I put my negative right there where you can see it. You could round that up to 37 because there's 2 significant figures, 3 significant figures, and you always go with the lowest number of significant figures when you multiply and divide, okay? So the 2 doesn't count because that's a constant, all right? So, so you could say 37 meters per second squared, okay? You could round it, all right? That'd be okay. All right. And now let's look at one more, number 47. We're still on chapter 2. And 47 is on page 68. All right, and I'll tell you what I may do. When I finish chapter 3, I may go back and give you all the problems. I'm going to shoot it to you in an email, though, so you should know. I'll shoot it to you in an email. All right? Okay. Because I think that would be better. That way you wouldn't have to rely on watching the videos. You would know, okay? All right. Okay, so number 47 says a gannet is a seabird that fishes by diving from a great height. If a gannet hits the water at 32 meters per second, which they do, what height did it dive from? Assume that the gannet was motionless before starting its dive. Okay, so let's label all our parts. So we got a bird. Okay, and here's the water down here, and we got a bird way up here. I don't know if I can draw a bird. Okay, that's horrible. There's his beak. Okay, all right, so he's diving. He's coming down, all right? And here's the fish. Okay. All right, there's the fish. He's diving after him. All right. All right, so it hits the water. So when it gets right here, all right, so when it hits the water, right just as it hits the water, its final velocity is 32 meters per second. Its initial velocity is 0 because it says assume that it starts from a motionless spot in the sky. In other words, it's just hovering, okay? It's just sitting there hovering and then it dives, okay? All right, so that's how we determine that. So we want to know what? Well, we know that, what is its acceleration? Well, it's going straight down. So its acceleration is actually equal to what? It's actually equal to negative 9.8 meters per second squared, correct? Okay? All right. Or we could just say 9.8, but we'll keep it negative and we'll see how things work out. All right, now watch. All right, so you say, well, how'd you know? Well, it's G. All right, acceleration is G. This is also G. All right, that's what it has to be, gravity, gravitational pull. Okay? All right. So it wants to know how far did it dive from. So from here to here, it wants to know, and since it's going down, we're going to say delta Y. Now listen, folks, the kinematics really don't change that much, okay? They really don't change that much from X direction to Y direction. The only difference about it is that it does this right here, okay? All right, so we have, if we're looking at it in the Y direction, V final squared in the Y is equal to V initial squared in the Y minus 2G delta Y. Okay? All right? And so we got to find delta Y, don't we? Okay? All right. So let's rewrite the equation. So delta Y is equal to what? V final squared minus V initial squared divided by what? 2G? All right. Is that correct? All right. Okay. So we plug everything in and we've got 32 meters per second squared minus 0 squared divided by 2 times a negative 9.8 meters per second squared. All right. And what do we get? So we get delta Y is equal to, delta Y is equal to, let's see here, we got 32 squared divided by a negative 2 times 9.8. And what do we get? What in the heck? All right, let me try this again. I've done something crazy again. 32 squared, all right, divided by, there we go. That's a whole lot better. We get 52.24. So we get 52.24 meters. Okay? All right. Now, let me ask you something. It says, let's go back and look at the question. It says, what height did it dive from? Okay? So what height did it dive from? Some of you are saying, now, wait a minute, Mr. Shields. This is supposed to be negative because that 9.8 is negative. Okay? Well, let me show you something. If you were to draw this on a Cartesian coordinate like this right here, and you say, okay, the bird's right here. This is where it starts initially. So its initial Y is what? Its initial Y is 0. And it's going to go all the way down to the surface. All right, there's the water, surface of the water. Notice that this is in the negative Y direction. Okay. Now, a couple of different ways you can look at this. You say, okay, I got a negative answer, but it's supposed to be in the negative Y. So let's see. If you've got a negative and a negative, it makes it positive, doesn't it? Yes, it does. Or you could look at it this way, and this is the way I should have looked at it. But technically, y'all, we always look at 9.8. We look at 9.8 being negative if you're going down towards the center of the earth. But it says what height did it actually, what was its height it started at? How high was it? So really and truly, we should look at it which way? Okay. Now, y'all, I'm not trying to confuse you, but I'm just trying to show you that either way you look at it, the negative cancels out. Okay, it cancels itself out. So we go back and look at it this way. All right, here's the surface. Here's the surface. This is Y and this is X. Here's the surface. And way up here's the bird. Okay, up here's the bird. and it's diving this way. All right, but we want to know what the height was. All right, in that case, G is not negative, but it is positive. So if you go back and make this a positive, guess what? You get a positive answer, which is what you should get. So either way you look at it graphically, you're going to get a positive answer. If you're wanting to know how high something fell from, if you're looking up and say, all right, how high was it when it started to fall? Then G is considered to be positive in that direction. Why? Well, look on your graph. All right, X and Y, X, Y. All right, look, gravity is naturally down, negative 9.8 meters per second squared. But if you're looking up and you know that gravity is acting on that bird, but you're up, then gravity has to be positive. You follow me? Because it's in the positive Y direction, okay? So again, you say, well, I thought gravity is always negative. Well, it all depends on your inertial reference frame. How are you looking at the problem? Are you looking up and seeing where it fell from, or are you looking down, okay? Or is it going down, all right? The object's going down, but again, we wanted to know how high above the surface was it. So you just change the answer to positive, okay? All right, little reasoning behind all the madness there, I hope. Anyway, all right, I'm going to pause again for a second and get ready for chapter 3. Okay, students, last one. Chapter 3. So now we're on chapter 3, and we're going to be on page 100. And we're going to look at problems 10, we're going to look at problems 14, 16, 28, and 41. So actually we'll be on 101 also too. I think 41. Yeah, 41's the last one. Okay. All right. So number 14, chapter 3, says Jack and Jill ran up the hill at 3 meters per second. All right. So we got a hill here, and I'm just going to do this right here. Okay. I'm going to draw it nice and straight. So they were going up the hill. Okay. They were running up the hill at 3 meters per second. So they were going that way. The velocity is equal to what? 3 meters per second. Okay. The horizontal component of Jill's velocity vector was 2.5 meters per second. So I'm going to say this is Jack and this is Jill. Doesn't matter. So I'm going to say that the horizontal component of her velocity was 2.5 meters per second, right? All right, you said horizontal, yeah, going in the X direction. What was the angle of the hill? Now, some of you may be saying, oh, dear Lord, what do I do here? Well, it's not difficult. Not difficult at all, okay? All right, so it gave us the vertical, it gave us the speed going up the hill, in other words, the hypotenuse, and it gave us also the X component. So that's the X component. So that's V in the X direction. I should have labeled it. Okay. Well, if you watched our videos and you went and you read through the chapter, you will see that when we have projectile motion, there's actually two parts to projectile motion, or motion in 2 dimensions. It doesn't necessarily have to be a projectile. You can be going at an angle like this, where you have 2-directional motion. Okay. Notice that the motion up the hill is 3 meters per second, but you got to realize that it's moving in the X and in the Y direction at the same time. So that's 2-dimensional motion. It's moving in the X and the Y at the same time. So we know to find the velocity in the X direction, it's what? Well, Vx in the X direction is equal to the velocity, the initial velocity, times what? Cosine theta. And to find the initial velocity in the Y direction, it's velocity times sine theta, right? Okay, so we've got to find the angle. So basically we've got to do what? We've got to solve this. We've got this and we've got this, but we've got to find that. So we got to do what? We've got to divide the, like this. Vx divided by V is equal to what? Cosine theta. And so theta then is equal to arc cosine, or inverse cosine, of Vx over V. So then for part A, to find the angle of the hill, theta, which is the angle, is equal to arc cosine, or inverse cosine, of Vx over V. And so we've got arc cosine of Vx, which is 2.5, divided by 3. And we get an answer of what? All right, well, let's see. So we got 2.5 divided by 3, and then take inverse cosine. And we get what? 33.5, 33.6 degrees, 33.6 degrees, or we could just say 34 degrees, okay? All right, real easy trig there, okay? And then it says what? What is the vertical component of Gilles velocity, all right? So we want to know the vertical component. In other words, we want to know Vy. So I've already told you how to find Vy. So B, we got Vy is equal to V sine of theta. And so Vy is equal to, what was V? It was 3 meters per second times sine of, what was the angle? 34 degrees, or let's do 33.6 since that's what it actually was. Sine of 33.6 degrees, and we get what? All right, well, let's do that. So we got 3 times the sine of what? 33.6, and we get what? 1.66, so we get 1.66 meters per second, or you could say 1.7 meters per second. You say, well, why can I do that? Well, because the lowest number of significant figures, well, you've got 1 here, but it's actually 3.0, isn't it? Yeah, I forgot to write that. Oops. So it's actually 2 there and 3 there, so you go with the lowest number of sig figs, it's 1.7, okay? All right, just to keep you on your sig fig rules. All right, let's do another one. Let's look at number 16, still on chapter 3, page 100, okay, page 100. Okay, and then it says you begin sliding down a hill, a 15-degree slope. All right, so you got a hill here, and you're on it, and I don't know, maybe you're on some skis or something, who knows. And you're going down this hill that way, and the angle of the hill, okay, the angle of the hill is 15 degrees, okay? It's 15 degrees, okay? All right, ignoring friction and air resistance, how fast will you be moving after 10 seconds? So, you're sliding down the hill, and of course we know that what's causing you to slide? Well, if you remember anything about physics, I'm sure some of you have had physics in high school, and we've already been talking about gravity because we talked about free fall. Then we know that gravity is pulling straight down, okay? You say, well, why is it not pulling this way? It doesn't pull at an angle, it pulls straight down. Even though it's on an angle, it's still pulling straight down towards the center of the earth, okay? And that's very, very important to remember, okay? All right, so what are we looking for? All right, let me go back again. It says, how fast will you be sliding after, 10 seconds, okay? How fast will you be going after 10 seconds? Well, there's a problem, isn't there? We don't know what the acceleration is, do we? It's actually going to be accelerating in this direction, isn't it? Okay? We don't know the acceleration, so we're trying to find the hypotenuse, aren't we? So basically what we can do then is we can say that the acceleration is equal to what? The acceleration of gravity, opposite over hypotenuse, is equal to g sine theta, isn't it? G sine theta. All right? Because gravity is pulling down the y, and so we plug in g, 9.8, and you just go ahead and plug in a positive. You don't have to worry about it being negative. Okay, because you say, well, why don't we make it negative? Well, because he's going down the hill, okay? You say, well, yeah, but that's still in the positive x direction. If you draw your Cartesian coordinate right here, it's still in the positive x direction, okay? All right, so we plug that in, and that's what? Sine of 15 degrees. And so 9.8 times the sine of 15 degrees, and what do you get? You should get 2.54 meters per second squared, okay? So the acceleration is 2.54 meters per second squared. And you say, how'd you know to do that? Well, I don't know my acceleration. All I know is the angle of the slope and the time interval. And by the way, how long, it says we want to know how fast will you be moving, so that we want to know what the final velocity is at 10 seconds, okay? At 10 seconds, right? Final velocity. Okay, well now we have an acceleration, don't we? So now we know what the acceleration is, 2.54, let me rewrite that, 2.54 meters per second squared. Okay, well, let's see, some of you ought to be thinking about your kinematic equations. So we got Initial velocity, what's the initial velocity? Well, this is what's in question. The initial velocity, we're going to assume it starts at 0, is 0 meters per second. We've got a time interval. The time interval is 10 seconds. Okay, so the time is 10 seconds. Well, do y'all remember this equation, this kinematic right here, VI plus AT? Yeah. So we want to know how fast after 10 seconds. Well, we got V final is equal to V initial, which is 0 meters per second, plus acceleration 2.54 meters per second squared times 10 seconds. And what do we get? We should get 25.4. So the final velocity is 25.4 meters per second. Okay. All right. It's just that simple, folks. Don't freak out. You got to think about what you have and then what you need and how can I get what I need, okay? Because it's not, for example, you said, well, how'd you know the acceleration? Well, I have to think about physically what's pulling that person down the hill. Well, gravity is. We're ignoring air, we're ignoring drag and friction. So the only thing that could be making that person slide is gravity, okay? And gravity pulls straight down. Well, I can find that. Look, opposite over hypotenuse, that is what? That is sine, okay? So I can find acceleration by saying g sine theta. And then once you have your acceleration, you've got your time interval, and you know what your initial velocity is. You start at 0, and you can find what it is 10 seconds, okay? All right, I hope that helps. All right, so now let's look at number 28, still on chapter 3. And we're still on page 100. And now let's look at number 28. I believe that's the right one. Yeah, 28. Okay. All right. So that was 16. Now let's look at 28. Okay. All right. It says a ball with horizontal speed 1.25 meters per second rolls off a bench 1 meter above the floor. Okay, so we got a bench, okay, like this, and we got a ball. And it comes off and does this right here. Okay, and there's the floor. And its velocity in the x direction is 1.25 meters per second. Now look, you say, how'd you know that? It says the ball with horizontal speed is 1.25 meters per second. Okay, and it rolls off. All right? So x initial when it comes off has to be 0, doesn't it? Yeah. All right? Sure does. Okay? 0 meters, all right? And of course, y initial is going to be 0 meters, okay? From here to here, this distance right here, from here to here is 1 meter. Actually, it's 1.0 meter, all right? 1.00, so it's 3 significant figures. 1.00 meters. There we go, all right? Okay. How long will it take for the ball to hit the floor? So we want to know how long will it take for the ball to hit the floor. Okay, well now we know what? We know a couple of things here. We know the velocity in the x. What's the velocity initial in the y? It has to be 0 meters per second because look, just as it comes off the table, it's not moving in the y direction. It's only moving in the x direction. And by the way, this x velocity, it does not change. It stays the same through the entire path, okay? The x velocity, when it comes off, you've got to remember your projectile motion. The x component of velocity, if we neglect drag, okay, we neglect drag, all right, then the x velocity stays constant, okay? All right, so it's not going to change. All right, now, okay, and your initial velocity, just as it comes off in the y, that's v in the y, and this is vx, and this is v initial in the y, okay, is 0 meters per second. All right, so we want to know what? From here to here, don't we? We want to know x, don't we? We want to know x final, right? We want to know x final. How far was it from the table? Is that correct? How long? No, that's one thing. How far was it? Yeah, okay. A is how long, let's see, let me read it again. How long will it take the ball to hit the floor? So from here to here, we want to know time. We got to find time. So A is time. Now you say, well, how in the world am I going to do that? Well, folks, we know G is equal to what? Negative 9.8 meters per second. Oh, shoot. Got too close to the edge. Meters per second squared, okay? G is negative 9.8 meters per second squared. All right, so let's look at this, okay? All right. Okay? Now, a couple other things we want to look at too. Notice that it's going from here to here. Okay? If you draw your inertial reference frame, notice that this is in the negative y. So that should be negative 1 meter, shouldn't it? Yes, it should. Is that the only place I wrote it? Yeah. Initial y is 0. Y final is negative 1 meter. Okay? You say, now how did you get that? Look, here's where it starts. That's the origin. It's going into the negative y direction. And remember, gravity is negative, okay? The math's going to work out beautifully. It's going to work out beautifully, okay? All right. So how do I find time? Well, if you go back to your kinematics, you remember this, that y final is equal to y initial plus vi in the y times the time minus 1/2 gt squared. Now look, you don't come in here and say minus minus. The minus is already in here. Minus 1/2 gt squared. And this is in the chapter. We've already covered all these kinematics in lecture, okay, on the videos, and you also find them in the text. It's not minus minus. The minus is already put in for me. You follow me? The negative there makes the g negative, okay? All right, so we got to solve for t, don't we? Now let me ask you something. What is the value of that variable there, those two variables going to be? Well, if the initial velocity in the y is 0, and you say, how'd you know, Mr. Shields? Look, just as it comes off the table, just as it comes off, and right as it starts to fall, its initial velocity in the y is 0. So watch what happens. That term is gone. And so now we're left with what? V final is equal to V initial minus 1/2 gt squared. All right, what is y initial? It's 0, so that term is gone. Okay? And so now let's solve for t, and so we solve for t, and we have to take the square root, and it becomes what? It becomes, multiply both sides by 2, and it becomes 2 times delta y, excuse me, initial y is 0. We could say delta y. 2 times y final divided by g. And now let's plug everything in. We got 2 times a negative 1, and that's 1.00 meters. Keep everybody happy. Divided by negative 9.8 meters per second squared. You can't take square root of negative. Cancels out, okay? Time is always positive. Time is always positive. I know some of you are thinking, yeah, but what about on a quadratic? If you have to use a quadratic equation, you always get 2 answers, and sometimes one's negative. I understand that. But, folks, we're not Michael J. Fox here. We're not going back into the future, okay? Or back into the past, okay? All right? There's no negative time. Time is always positive. So we get an answer of what? So we got 2 times 1, which is 2. 2 divided by 9.8. And then take square root of that. And what do we get? We get 0.452 seconds. 0.452 seconds. It's positive. Those negatives cancel out. So that's how long it took to hit the floor. Okay? 0.545. And you say, why'd you go 3 sig figs? Okay, why'd you go 3 sig figs? Well, because there's 3 right here. That's a constant. Okay, that's a constant. All right. You don't, when you typically, actually I probably should have written 9.80. There should be a 0 there. So now we got 3 and 3. 3 sig figs and 3 sig figs. Okay. My bad. Okay. Or you could have said 0.45. That would have been close enough. All right. Now let's look at B. Whoops, let's look at B. All right, so 28B, all right. And it says what? How far from the point of the floor directly below the edge of the bench will the ball land? In other words, and I've already drawn this out, in other words, from the edge right here to here, how far out from the edge of the table where it came off the table will it land? Well, I have no idea, Mr. Shields. Okay, now look, if you remember that velocity is equal to delta x over delta what? Delta t, right? Okay, so let's break this thing apart now, all right? One of your kinematics is this right here. X final is equal to x initial plus v vi times t, right? And you say, where does that come from? It comes from this equation right here. You take this, make it x final minus x initial, all right? Okay. You with me? I hope everybody's with me. You solve for delta x. Y'all, it's there. You just got to do the math, all right? So let's plug everything in. So we want to find x final. What was x initial? Well, x initial was 0, wasn't it? Go back and look. Remember what I said. The starting point right here is 0. Okay, that's where we're starting from. It's just as it comes off the table. So that's 0 meters plus the initial velocity was what? What was the initial velocity? 1.25 meters per second? 1.25 meters per second. What was the time? We just calculated to be 0.452 seconds, not meters per second, seconds. Okay, right? Hopefully everybody's with me. And what do we get? So the final x is what? Well, we got 0.452 times 1.25, and we get 0.565. So we get 0.565 meters. That is how far from the edge of the table the ball will land. Okay? Okay, I hope this is making sense to you. You can't panic on these, folks. You just got to think about them a little bit, okay? You got to think, okay? All right? As Colonel Stamper used to tell us, you got to think. God forbid, but you got to think a little bit. All right, and now let's look at one more, number 41. And this is still chapter 3, and this is on page 101, all right? All right, it says a particle rotates in a circle with centripetal acceleration. So we got a circle, and we got a particle right here, and let's just say it's going that way, all right? And it's rotating in a circle, and its acceleration is what? 8.0 meters per second squared, isn't it, okay? All right, so we got a particle in a circle with centripetal acceleration of 8.0 meters per second squared. What is A if the radius is doubled without changing the particle speed? Okay. Now this is really a conceptual question. All right. Well, first of all, we got to remember what centripetal acceleration is. By definition, centripetal acceleration is the velocity squared divided by what? The radius, isn't it? Okay. So if we keep the velocity constant, if we do not change the velocity, and we double the radius, okay, so in other words, if r goes to 2r, what happens? Well, look at your equation. If you're at 1 here, and this is constant, and then you go to 2, it becomes 2r. Then what happens to the acceleration? The centripetal acceleration is 1/2 of a. It goes to 1/2. Come on now. It goes to 1/2. It's cut in half. You say, how can that be? Look, y'all. Look, it's inversely proportional. Radius is inversely proportional to the acceleration. If you keep that constant and you double the radius, then you cut the centripetal acceleration in half. Okay? That's easy. All right, now watch. And then look at part B. The speed is doubled without changing the circle radius. All right, well, centripetal acceleration is equal to what? V squared over R. All right, so then if V squared, it becomes 2. Ah, shoot. If the velocity then goes from V to 2V, forgot to put my phone on vibe, sorry about that. V to 2V, all right, we'll plug it in. Well, centripetal acceleration is equal to 2V squared over R. Well, what's 2 times 2? It's 4 times as much. 4 times the centripetal acceleration. Right? Sure, do the math. That's conceptual. 2 squared is 4. So whatever the velocity is, it'd be 2 times that divided by r and be 4 times the original centripetal acceleration. Okay, folks, I hope this helps you.